Okay. Any questions about anything? And by the way, to the VideoNote people, we're having a test tomorrow. Will you be in touch with the powerful people at VideoNote between now and then? I keep forgetting to send Danila an email, but anyway. Okay, or Danila, or however you say his name. Yeah, so the guy doesn't show up tomorrow. You know, he came last time, and we thought about doing sort of a fringe film, you know, like a cult experimental film, people taking a test, but we decided that wouldn't pass muster. Okay, any questions? Yes, David. Circular convolution is not covered on this prelim. Nothing after the regular old, you know, the whole sampling thing. Not the DFT, and not the FFT, which we're going to talk about today. But any other questions? I passed just now walking across the bridge, Manish and Balaj, going back to their house at 218 Delaware with copies. No, I walk by there every day, so I know where they live. With copies of last year's prelim 2 to I presumably work on during class time. So they assured me that they would watch the video notes at some later date. So hi, Manish and Balaj. It's good to see you today. Oh, and hi, Ricardo. Why are you all the way back there? You just want to make sure I don't say anything about the test, and yeah. And there's a couple people who are going on soccer trips who are going to take the test today, so they're going to find all the bugs for us. They're going to help us out. Yes, Stephen. Pulse sampling and time division multiplexing are fair game. Any other questions? Essentially through the end of the chapter that is titled the DTFT and sampling. But no wavelets? No wavelets on this test, no. I know, sorry. Any other questions? Rohit? Sorry?
What's your favorite meme?
My favorite meme? Oh, holy moly. I don't know. It has no cats in it, okay, for one thing. Did you notice that some people put up some popular memes on Piazza today? Amanda?
I did the LOL.
You did the LOL. No, so I had to look it up. What did I do? I was sitting in... Right. Well, you put the trauma one up, and then someone put up this one from Futurama. Okay. So, yeah. So anyway, I had to look it up. So I typed in, not sure if trolling, into my Google search window. And immediately up popped a zillion images of that guy, squinting. And they said that the meme pattern, the sort of the DNA of the meme was not sure if X or Y, something to that effect, or maybe Y. And so then I thought, well, wait, no, this is very specific because lots of these pictures say not sure if trolling. So I have to find out what not sure if trolling, why is that a popular first line of this meme implementation? Okay. And I still haven't quite figured that out. I apologize for that. It's probably a generational thing. Maybe Ricardo can help us out. No? Okay. Anyway, good. I like it when people use Piazza. I try to answer as quickly as possible. As soon as I see the email, if I'm near, if I have time, I try to answer it right away. So I don't know. To answer Rohit's question, I'm not sure what my favorite meme is. Do you know where the word meme came from? Who originated it? Richard Dawkins, who is a noted, forget about his polemicist, sort of atheist, whatever thing that he's known for now. He is a famous ethologist, animal behaviorist, evolutionary theorist, and all that stuff, and he's written some amazing science books. that have nothing to do with science versus religion, that have to do with science. And he invented the word meme to sound sort of like gene as a unit of cultural inheritance. In some sense, something that can mutate from one cultural generation to the next. You know, if somebody makes up a cool saying. What are you laughing about, Nathan? Your mind's being... No, this is cool. You know, if you look up the word meme, and he invented it. He invented it in the book called The Selfish Gene, which came out in the 1970s, which pitched a sort of a gene selectionist level of evolutionary natural selection, which is slightly an oversimplification, but I think it's really compelling. I think the best science book I've ever read is his book called The Blind Watchmaker, which is about evolution. It's really an awesome book. I recommend it to anybody. Okay, so any other questions before we talk about the FFT? Okay. And this chapter, like I said, is almost ready. The revised version, I think it's a lot cleaner. Oh, somebody did a sloppy erasing job here. Okay, so last time we talked about some sort of elementary applications. As soon as I turn my back. He's out the door. Okay.
When you started writing the call, he just leaves.
Yeah. I guess he's sick of this. Sick of this whole... Oh, the really lengthy exam review. Yeah, right. I'm not an exam review type person. You know, what you want to do is you want to badger your TAs. Say, hey, would you guys do a, you know, see what they say. They're under no obligation, but anyway. So some applications of the DFT, and what makes them interesting as applications is that they reduce other computations in computing endpoint DFTs and doing elementary other stuff with what you get. And they're interesting because of fast algorithms for computing DFTs and inverse DFTs. And that's what we're going to talk about today. And these fast algorithms are known as FFTs. Fast Fourier transforms, but no one ever calls them that. Like if you run into someone on Hope Plaza and they say, did you learn about the fast Fourier transform yet? You'll know they're a space alien because any human or just calls it the FFT. Okay? So fast Fourier transforms. And the originators of this idea, there's a lot of sort of debate about whether it goes all the way back to Gauss, you know, in some sense. That's all revisionist history. Really, they're due originally to Cooley and Tukey, two Bell Labs guys. We've talked about Tukey briefly before. I'm not sure whether in this class. I know we talked about him last spring a little bit. He was the one who allegedly originated bit, the word bit, for binary digit. So he's come up with a lot of interesting ideas. And I want to emphasize that there's not just one fast Fourier transform, not just one FFT, there's many of them. And we're going to talk only about one. They all have the same essential structure. And the structure hinges on this idea of splitting things up, dividing and conquering is what people like to say. And so let's see how this goes. Okay, so what we're going to consider in this class, what I call the decimation in time endpoint, no, decimation in time FFT for computing the endpoint DFT of an endpoint signal when n is a power of 2. So n is 2 to the L for some positive natural number L. And the other kinds of FFTs you see are ones called, like, for example, decimation in frequency FFTs. That's another way to do it. Or FFTs for computing endpoint DFTs of endpoint signals where n has the following prime power factorization, and so on and so on and so on. But they all pretty much come about in the same way as this one does. Okay, so starting point is you're given a signal. So you're given n equals 2 to the L and some endpoint signal S. So X is in the set Sn of endpoint signals. And your goal is to compute the endpoint DFT of X. Okay. By definition, we know the following holds true, that X hat sub k, these are the values of the endpoint DFT R, is given by the sum from n equals 0 to n minus 1, x of n, psi sub n to the minus nk, for 0 less than or equal to k less than n. That's the definition of the endpoint DFT of X. It's those n numbers, x hat sub k, you get by that. And here, of course, psi n, as always, is e to the j 2 pi over n. Now, I want to make an observation about this. First of all, to compute the endpoint DFT using this formula for each x hat sub k, that's what we're going to call direct computation of the endpoint DFT. How many multiplications does that require nominally? Okay, so think about that. So computing all these x hat sub k, 0 less than or equal to k less than n, directly from this equation. And in fact, there's not just one equation, there's n equations, requires, and to be fair, some of these are trivial multiplications, but how many? How many multiplications does it require? N, someone said? Well, if I want to compute x hat sub 1, say, how many multiplications does that require? X hat sub 1 is the sum of a bunch of products. How many products are in that sum? N, actually. So every single x hat sub k takes n. Since there's n of them, computing all the x hat sub k's takes n squared multiplications. And as I said, to be honest, and of course you all know, I hope, that multiplications are the things that take a long time in computers. When people are counting operations in a computation, they don't count the additions, they just count the multiplications. And to be fair, as I said, some of these are trivial. Like, for example, when k equals 0, all the psi n to the minus nk terms are just ones. So all you're doing is computing a sum. So those multiplications don't really count. But I'm just taking them into account here as part of the nominal number of multiplications it takes to compute the DFT directly from those equations. Okay. So what I'm going to do is define two n over 2 point signals. And one of them I'm going to call x sub e, and one of them I'm going to call x sub o as follows. X sub e is just going to be the n over 2 point signal I get by looking at the even indexed x values. So x sub e of, and let's use m for the index here, is equal to x of 2m for 0 less than or equal to m less than n over 2. And remember, n is a power of 2, so n over 2 is, again, an integer. And xo of m is equal to x of 2m plus 1 for the values of m in the range 0 to n over 2 minus 1. So what is XE? XE is an n over 2 point signal that comprises the even indexed values of x. So XE is an n over 2 point signal comprising the even indexed x values, and XO is similarly an n over 2 point signal comprising the odd indexed x values. That's a simple thing to do. And what I want to do is I want to go into this sum defining x hat sub k, and I want to split it into even index and odd index terms. So note that x hat sub k is equal to, you can take that sum from 0 to n minus 1 and split it into even index terms. So the sum from n equals 0 to n minus 1, where n is even, x of n, psi sub n to the minus nk, plus the sum from n equals 0 to n minus 1, where n is odd, of the same thing. And that's still true for all k. And if you re-index the first sum, setting n equals 2m, you get this. X hat sub k equals the sum from m equals 0 to n over 2 minus 1, x of 2m, psi sub n to the minus 2mk, plus the sum from m equals 0 to n over 2 minus 1, x of 2m plus 1, psi sub n to the minus 2m plus 1k, still true for all k. And x of 2n is just xe of m. And what is psi sub n to the minus 2mk? Here's a key observation. What if I take psi sub n and I raise it to the second power? What do I get? Look at the definition of psi sub n up there. Yeah, well, it's e to the j 4 pi over n, but it's also e to the j 2 pi divided by n over 2. Why did I write it that way? Psi sub n over 2, right? Okay. So psi sub n to the minus 2mk is psi sub n over 2 to the minus mk. And over here, sum from m equals 0 to n over 2 minus 1, xo of m. And here it's going to be, I'm going to factor a psi sub n to the minus k out of every term. And in here, I'm going to have, again, psi sub n over 2 to the minus mk. What is this first term here, this first sum? What is that in terms of DTFTs? Alex? Yeah, a DFT. Yeah. This sum almost, and I'll tell you what the almost is in a second, is the same as xe hat sub k. In other words, the value at k of the n over 2 point DFT of the n over 2 point signal xe. This one here, similarly, is almost xo hat sub k. The reason for almost is that this expression for x hat sub k holds for all k up to n, but the n over 2 point DFTs of xe and xo are defined only for k going up through n over 2 minus 1. So we have to be a little careful here. So this almost says that x hat sub k is equal to x e hat sub k plus psi n to the minus k, nk, or minus k, right? Psi n to minus k, x o hat sub k, 0 less than or equal to k less than n, but not quite, because x e hat sub k and x o hat sub k are defined only for k's between 0 and n over 2 minus 1. And this expression holds for all k's all the way up to n. But that problem disappears. What? Less than, yeah. Thank you. You can always just say, did you leave out a thing? You know, you don't have to laugh and have me look. You know. Denzel?
Can you please explain why there's a sign n to the minus k multiplied by the x?
Okay, let me get the, where's the pointer when I need it? Where? Oh, it's too far. This term here, okay? I need to have just psi sub n to the minus 2 mk to make this happen. So I factor out a psi sub n to the minus k. Thank you so much. Okay. So now we have a pointer at the ready. I thought I was going to have to go up to board number 2. But that's board number 1, that's board number 2, that's board number 3, by the way. All right. So how do we solve this problem? It's easy to solve because if you take a k that's between n over 2 and n minus 1, so the problem disappears. Because of y. Because when n over 2 is less than or equal to k and is less than n, those are the criminal values of k in that first expression, we have the following. That psi sub n over 2 to the minus mk equals psi sub n over 2 to the minus m times what? K is between n over 2 and n, so it's n over 2 plus k mod n over 2. And what is psi sub n over 2 to the n over 2? Fast? 1. Psi sub anything to the psi sub thing to thing equals 1. Right? So that doesn't contribute, and all we have left is psi sub n over 2 to the minus m times k mod n over 2. All right? So the conclusion is x hat sub k for all k, and this requires just a teeny bit of a manipulation, I'm just going to write it down this way, equals x e hat sub k mod n over 2 plus psi sub n to the minus k x o hat sub k mod n over 2 for all k. 0 less than k less than n minus 1 less than n. And the reason this holds even for the k's down to 0 is that k mod n over 2 is going to be k for those k's. Now, the details here are not as important as counting up how much we've saved by doing this. And you may say, well, wait, what have we saved here? What we've done is we've turned the computation of an endpoint DFT into two different computations, one after another. So thus, to compute the endpoint DFT of x, what you do is first compute the n over 2 point DFTs of xe and xo. Those are n over 2 point signals. And let me give this equation a name. Let's just call it star. And then you assemble them by means of equation star to get x hat sub k for all k. Okay, so that's something I hope everybody understands, because this is the key step. This is it. To compute an endpoint DFT, when n is a multiple of 2 even, but in this case we're assuming it's a power of 2, you first compute two n over 2 point DFTs and then assemble them by means of that equation over there. Computation-wise, what does this do? We've observed already that the direct computation of x hat sub k nominally requires n squared mults. And assuming we compute those n over 2 point DFTs directly, each of them is going to nominally require n over 2 squared mults. Putting them together by means of star requires n mults. Okay? So the direct x hat sub k computation requires n squared mults. And what we've done is we've turned that into 2 times n over 2, the quantity squared. So these are direct comps of xe hat and xo hat plus n. And this is the assembly by means of equation star, because there's n equations here, one for each k, and each of them requires a multiplication by psi sub n to the minus k. And if you do the math here, you see that this is the same as something. N squared over 4 times 2, so it's going to be n squared over 2 plus n. Mults. And you say, well, wait, there's still an n squared in there, but n squared is bigger than that, because n squared over 2 is bigger than n. So that's fewer. And it would be pretty dumb just to stop there, because, yes, Nathan? No. We're assuming it's not a 1 point signal. 2 to the 0. L equals 0, right. Okay. Now the thing here is that we're not going to stop there. We're not going to stop there. Recall that since n equals 2 to the L, n over 2 is still a power of 2. So we can turn each of those n over 2 squareds into 2 n over 4 squareds. So each n over 2, the quantity squared, becomes 2 times n over 4 squared plus n over 2. In the same way that plain old n squared became 2 times n over 2 squared plus n. So now we're down to how many multiplications? Twice quantity 2 n over 4 squared plus n over 2 plus n. And if you do the math out, that becomes 4 times n over 4, the quantity squared, plus 2n. And I'm going to leave it like that for now, because we're going to keep doing this. The n over 4 squareds are going to become 2 n over 8 squareds plus n over 4. So you keep this up. That is to say, well, let's just say, for example, the each n over 4 squared becomes 2 n over 8 squareds plus n over 4, etc., etc., etc. Has anyone ever had a class from Jose Martinez? Does he say that? Etc., etc., etc. And does he also say, at the end of the day? Yeah. There's one more Martinezism, and I'm trying to remember what it is. I don't remember that. Yeah. But those are the main ones. At the end of the day, you know, et cetera, et cetera, et cetera. Okay, so you keep this up. You keep this up. And notice what's happening to the term inside the parentheses every time. What?
My favorite quote from Martinez was, "You can tell by my accent that I'm not from here, from New Jersey."
Can you tell from my accent that I'm from New Jersey?
Can you tell from mine that I am?
No. See, most people, a lot of the real New Jersey accent turns every vowel into a diphthong, and every diphthong into like a 4-part diphthong. You know, like instead of saying oh, you say oh, oh. And day becomes day, day. See, there's like 4 steps there. Anyway, but I don't think I talk that way. Do I? No? Okay. Anyway, you keep doing this. Look what's happening to the term inside the parentheses. The term inside parentheses becomes n over 4, n over 8, n over 16, blah, blah, blah. Sooner or later, it's going to get up to n over n. So it's going to be a 1. And what's happening to the term in front of the squared term is it's going up by powers of 2. So it leads eventually, after L steps, capital L steps, to 2 to the L times n over 2 to the L plus Ln. Because every single time you do another step, you add on an n. 2 to the L times n over 2 to the L is just n. L is log to the base 2 of n. So that's what happens at the end of the day. Okay? So this is the reduction. Oh, he asked a very good question. Denzel asked a very good question. What happens in the real world when you have an odd-numbered signal? Does anyone have a suggestion? How do you make it even, Ian? Zero padding. Yes. You take your say 5-point signal. Well, you never use this for a 5-point signal, but take it to your 5-point signal and you pad it with 3 zeros and just think of it as an 8-point signal. That's how you do it. Go up to the next power of 2. Nice is correct. This is a really cool thing. This is basically, I don't know. I mean, I can rhapsodize about this just like I do about the sampling theorem, but I won't. So anyway, the bottom line is that by doing this nice thing, n squared mults becomes n plus n log n mults. And anybody who's ever studied computational complexity knows that that's a huge reduction. N log n is way less than n squared. And to put some numbers to this, suppose you have like a 1024 point. Yes, Rohit. Yeah, squared. Let's put a squared on there just to. Thank you. So suppose you have a 1024 point signal, a 2 to the 10th point signal. So for example, n equals 10 to the 1024, which is 2 to the 10th. Then n squared equals $1,048,576, I think. Check that for me, will you? It's something like that, okay? And what is log to the base 2 of n? So n plus n log n is equal to 1024 plus 10 times 1024, which is that. And that's just 11,264. So what do we got here? We've got a factor of 100. We've got essentially a 2 orders of magnitude reduction in the computation. And that just gets better and better and better the larger n gets. Now, I'll let you think about that, and then I'll draw some pictures after the 3-minute break. I'm going to check that 1024. Not faith, but like confidence or something that you want to. All right? Okay. All right. So what is this picture here? You don't have to copy this now. It's on the monograph, or it's on the Blackboard website, and it will be in the monograph someday. It's a classic picture of this computation. So this shows how things look when n equals 8. And we're going to look a little bit more detailed at this picture, but the idea is that the x values come in the left side and the x hat values come in the right side. What this picture is something called a signal flow graph. And I haven't polluted it by putting labels on the branches, but I will in a second, or I will sort of look at it, zero in on it microscopically. It's a signal flow graph. The idea is that the signals flow left to right and along the branches and get summed at nodes. So nodes are summers, and each branch has a coefficient multiplier that multiplies whatever comes in to the left end of the branch times that coefficient So it has a coefficient, and it multiplies, quote unquote, incoming to get outgoing. And what I want to do is I want to magnify a couple of these pairs of branches to show you what is going on. So, for example, let's just look at the beginning of the diagram. Let's look at the one that connects, say, 2 and 6. So x of 2 and x of 6 go like this. To give you whatever they give you. And this is going to be psi sub 1, or psi sub 2, to the minus, let me think a second here. I know this is 1, and this is 1 as well. This is psi sub 2 to the minus 3, and this is psi sub 2 to the minus 1, and this is psi sub 2 to the minus 3, I think. Let me think a second. Oh wait, I should have made sure I knew what a couple of them were before I came today. That's x hat e sub 2. I think I have one written in the monograph, so I can tell you what it is. I'm sorry about not memorizing one of them before class today. But the left half of the picture, notice that the values going into the top half of the left half of the picture are the values of x sub e. The values going into the bottom half of the left picture are the values of x sub o. The numbers at the nodes, the first node you get to the right of the original nodes, are going to be x hat sub e up top and x hat sub o down below. Anyway, I'm not going to bother telling. It's on the. Anyway, these all have psis on them. These have the ones coming from the upper ones always have 1s, and the ones coming from the lower ones always have psi to some power. And there's a nice general form for that. So it's going to be psi sub something to some power, and this is going to be psi sub the same thing, but to a different power. This one is going to be, say, something, and this is going to be something plus something. So a different power up here. And you can figure out what those are by going through that computation and all. And the middle, as I said on the left, the top half computes x e hat. The bottom half computes x o hat. And the assembly of x e hat into x hat occurs on the right half. So this is on the left, also on the left, and the right side assembles xe hat, and this one I can give you what the size are, and xo hat to x hat. And e.g., let's look at an example of one of these things. Let me get this one right here. How about x hat sub 1 is going to equal something times x hat e sub 1. So it's just going to be xe hat sub 1 plus psi n, so psi 8 to the minus 1 xo hat sub 1. And the other piece that goes along with that is going to be x hat sub 5 equals, and that's going to give us xe hat sub 5 minus 4, which is 1, plus psi 8 to the minus 5 xo hat sub 1. Right. So that's how x1 hat sub x hat sub 1 and x hat sub 5 get assembled from xe hat sub 1 and xo hat sub 1, which are the things at the respective positions down there. So anyway. All right, so this diagram looks like this. You have xe hat sub 1 and xo hat sub 1 getting assembled in this fashion. These are both 1s. This is psi 8 to the minus 1. This is psi 8 to the minus 5. And you had xo hat sub 1 and x hat sub 1 and x hat sub 5. Okay, so I got that one right. I knew that one. But this one I was screwing up. Okay. Now, you may notice that all these computations look kind of the same, right? You take two things and you mess with them and you get two other things, right? Now, those of you, I know, Will's not here, is he? But you are, James is. You, the Dorshak people. You did this in 2200, right? You forget?
I forget.
Well, Will said you did.
Okay, I guess we did.
Okay. But you know, I don't know how much depth you went into it. But the point is, there's something to note about this that points up a further economy. In addition to this raw reduction in multiplications that the FFT introduces computationally. So, observation is that every FFT computation takes a pair of numbers at one stage and combines them by one of these little diagrams. And these diagrams, does anyone know what they're called? So there's a name for these diagrams because of the shape. I'm surprised you haven't heard this before. This is sort of one of those common knowledge type things. Hourglass, close. Butterfly. Okay. By a quote unquote butterfly, this is that takes, so it takes two numbers and it combines them with some coefficients or another. I don't know what they are, but yeah, Stephen.
Shouldn't the value of x hat as some k for any k have all the values of x?
It does, but this disassembly of it.
So I think we're missing like a step there.
Are we missing a step? We might be missing a step.
I think it's a butterfly between the bottom half and the top half.
No wonder it was so small up there. Oh, we should probably wipe off this whole part of the lecture.
Because the way it is there.
Yeah. You have to. Oh boy, I screwed this. I big time. I'm trying to think of a way to salvage this. Okay, here's what I'm going to do. folks at home, okay. And you guys can listen in on this too. Okay. What I'm going to do is I'm going to draw the correct butterfly diagram for n equals 8. It's actually already on the website, but I'm going to put plenty of commentary on it, right? And so everything from here, it's not actually that much. It's just from the butterfly diagram to here, okay, this is all messed up. So put a big bracket around it in your notes, and you'll be able to fix that later when you have the correct diagram. But everything I'm about to say applies to the correct diagram, okay? Is that fair? Is that fair? I guess I'm just worried about the prelim, right? Anyway, okay, so I do want to tell you today, I want to tell you, I don't want to try to fix this butterfly today, this diagram today. What I want to do is I want to tell you what's good, in addition to the raw reduction and multiplications, is this, that every computation you do takes a pair at one stage and combines them by a butterfly to a pair at the next stage. And if you think about it, the location of the pair that you combine and the location of the pair that you get by combining them are the same. If you think of each stage as manipulating the numbers in some shift register, right? These two numbers get manipulated to give the same two numbers. And all the other ones are that way too. And therefore, the computation takes place in a fashion that the computer science person would say pairwise and in place. Because, for example, you can see that, okay? And it's going to be true even with the complete diagram. And what that does is it makes this FFT perfect for parallelization, right? Because you can do all these little pairwise computations simultaneously without referring to the other little pairwise computations you're doing. So it combines them via butterfly diagram into the numbers at the quote-unquote same two locations at the next stage. So the terminology here is pairwise in-place computation. And like I said, this is ripe for parallelization. And I'm not sure whether this has two L's there. I know it has two L's at the beginning, but I'll just put two L's in there anyway. Okay, so that's thing number one. That's another computational economy that you get from this. Second thing is, what, is something missing? Oh, pairwise. Yeah, pairwise in-place computation. Another thing is that, and even when I do put up the correct diagram, look at how the x values get permuted. You have to permute the x values before you start this computation to get them in the right order to go in the left side. Right? The top four have to be xe, but they also have to be xe arrayed in a certain order. So note that you need to permute the x values so they're in the right order to enter the left side of the computation. Now, one might think that that permutation is complicated. You know, to turn 0, 1, 2, 3, 4, 5, 6, 7 into 0, 4, 2, 6, that's only going to get worse and worse and worse when n gets larger and larger and larger. So how hard is that for large n? Well, let's look at the n equals 8 case. And what I'm going to do is I'm going to write down the index of the x value for each of those x values from top to bottom in order. So here's the index of the x value. And I'm going to write them down in binary. So 0 becomes 0, 0, 0. 4 becomes 1, 0, 0. 2 becomes 0, 1, 0. And 6 becomes 1, 0, 1. And 1 becomes 0, 0, 1. 5 becomes, oh, I messed, this is 1, 1, 0, right? 5 becomes 1, 0, 1. 3 becomes 0, 1, 1. And 7 becomes 1, 1, 1. So that's the index of the x value. And here I'm going to put down the position in the array in binary. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, does anyone see what's going on there? Not Alex. Maybe some other Alex. Denzel.
It's like the mirror image.
The mirror image, yeah. All you do to get the x's in the correct order is do a bit reversal on the indices. Okay? So to get the correct input order, you just do a bit reversal on the indices, and that turns out to be easy. And it turns out to hold for all n. You can prove that. All n of the form 2 to the L. So that's another economy. To arrange the things before they go in does not require a complicated shuffle. And so you can imagine you have this array, and I don't know. Whatever data structure you're using is going to determine how you do that, but you get the idea. And one final little economy. So one final sort of smallish economy. Every butterfly looks like this. Turns out to look like this. It's going to have ones on these branches and then it's going to have some power of psi here, psi something to the, say, q, and here it's going to have that same psi, the same something to the q, but with a minus sign in front of it. So it's going to have a 1, a psi, and a minus psi power. And so what you can do is you can, in some sense, you can factor that psi power out, and you get a super simple butterfly, like so, that has ones here and a minus 1 here, and pre-multiplied by the psi power to the q here. And so you could build these simple butterfly, computers and pre-multiply by the appropriate psi powers, and that's what you get. So what that does is it it takes nominally 2 multiplications and turns it into 1. So it's yet another economy. So this is all great. This is all great stuff. Furthermore, we know that we can think of endpoint DFTs and the whole analysis we've done of endpoint signals just in terms of matrices, vectors, and all that sort of thing, right? So what does this business tell us? Let me just make sure there's no other economies. I'm still rattled by putting up a bad butterfly diagram, so I might be forgetting something that I wanted to tell you. Nope. Okay. Now we can erase the offending diagram. What is this in terms of matrices and stuff? Clearly, we're talking here about endpoint signals and doing computations with them. Before, when we talked about endpoint signals, we talked about their spectra and sampling their spectra to get the endpoint DFT. But on the other hand, we could just think of it as vectors and multiplying a vector by a big matrix psi, all that. So how does this shake out? So here's a question. What's the sort of the linear algebra interpretation of the FFT? Okay. So the direct computation of the DFT in linear algebra terms is this. It's vector x hat equals matrix psi sub n times vector x. So this is in the world of CN, in the world of linear algebra, this was our characterization of computing the endpoint DFT of an endpoint signal x. You put the vector, you make the vector little x be the vector of values of the signal, and then the vector x hat is going to be the vector of values of its endpoint DFT, and psi sub n is appropriately defined. Okay, so what is the FFT in linear algebra? It turns out to be a factorization of psi sub n into the product of relatively sparse matrices. So FFT factors, so FFT is equal to, it's congruent to, so to speak, in linear algebra terms, a factorization of psi sub n into quote-unquote relatively sparse factors. And what I'm going to do is, in the time that remains, I'm going to show you at least one stage of how that works. Wait. So, for example, one stage, the end stage of the 8-point DFT. So let's look at it for n equals 8. The last stage, what that does is it, first off, it takes the 4-point DFT of XE and XO and assembles it. Well, I don't even know if you want to call it the first stage. Let's characterize it this way. For n equals 8, our first quote-unquote reduction step entailed taking, so we have to change takes to taking to make the grammar correct, the 4-point DFT of XE and XO, and assembling them. Okay, so what does this correspond to in matrix terms? First, we have to take the vector x and permute it so xe and xo are there. Then we have to multiply xe and xo by psi sub 4 to get the xe hat and xo hat. And then we have to assemble them together. So here's my signal vector x. Let's see how far I can get with this. And if I take that vector and I multiply it by this matrix, what's that going to give me? That's going to give me xe up top and xo at the bottom. All I've done is I put ones in places to pluck out the even values first at the top and in the appropriate places to pluck out the odd index values at the bottom. Then what I have to do is take that and multiply it by psi 4. So you multiply that vector by this matrix. It has a psi 4 in its upper left-hand corner and a 0, a 4 by 4 matrix of zeros here and here, and a psi 4 down in the lower right-hand corner. What that's going to give you is this. A vector that has xe hat at the top and an xo hat at the bottom. And then finally, you multiply that by the assembly matrix, so to speak. And what is the assembly matrix going to look like? So you can see that's a sparse matrix. That's relatively speaking sparse. It has just half as many entries that are non-zero as capital Psi. And the assembly matrix is just going to have 2 non-zero entries in each row. And it's going to look like this. 1. And then something like this. So you can see there's lots and lots of zeros, as you would expect in a sparse matrix. And if you multiply that last vector you get that had xe up top and xo at the bottom, you get x hat vector. And then the next step is to pare it down even further. You the first thing, the computing the psi4s, you look underneath the, anyway, you get the point. It's too late. I can't continue without taking up too much of your time. But anyway, linear algebra-wise, the FFT is just matrix factorization. That's it. And so let's leave it at that for today. And see you tomorrow at the prelim, I hope.